for this chapter 9. And this one here, it is a two-dimensional problem. And then here we have two billiard balls moving. The first one is moving with 3 meters per second in the x direction. It strikes an equal mass ball, B initially at rest. Then they are equal. Then I can say MA equals MB. The two balls are observed to move off at 45 to the x-axis. Ball A above the x-axis and ball B below. What are the speeds of the two balls after the collision? Okay, now they have equal angles here, and this is actually the situation. After this is like from here to here, it is before, and then here this is after collision. And we have, of course, x and y just to show you. Now conservation momentum here, it's gonna be in two dimensions. For the x-axis, it will be MAVA cosine A plus MBVB cosine VB, and equals, this is before, equals after MAVA prime cosine theta A prime plus MBVB prime cosine theta B prime. Okay, equal masses. This is gonna make me cross all the masses. Also, the first object was moving horizontally like this, then cosine 0 and cosine 0 is 1. And the velocity of the second one was 0, then my equation is going to be this one, and then I can plug my numbers in it, and this is number 1. For the y direction, I will repeat the same equation, but for the y, MAVA sine theta A plus MBVB sine theta B should equal MAVA prime sine theta A prime plus MBVB prime sine theta B prime. And here I can end up with concluding that the two velocities should be equal. And this is making sense since one of them is 45 and the other one is negative 45. Then I will say they're gonna be equal so that the velocities in the y direction will cancel. I can rearrange my equations and solve 1 and 2 to have my velocity 2.12. For the sake of significant figures, I can put this as 2.1 meters per second. Okay, this is in a nuclear fission, where fission means that there is a heavy nucleus that is going to split into two nuclei. And in our example here, we have uranium that is going to split into two unequal fragments. One of them is light and one of them is heavy. And we are asking about which fragment has the greater momentum. Obviously, the uranium was at rest, then the momentum after should be at rest. Then the change in the momentum of the heavy is going to equal the change in the momentum of the light. And since they were initially at rest, then both momenta, they should be the same. Momenta is different from velocity. Okay? The second question is asking which one is going to have a greater speed. Now, of course, here we are going to have, because it is mv, m times v, then, and these two equal momenta, then the one that is light, the one that has less mass, is going to move faster. We know that for sure in nuclear physics. All right. Now, the idea of center of mass, the center of mass of a system is the point where the system can be balanced in a uniform gravitational field. and is going to be always, that point is going to be towards the heavier part of the object. And this explains why our center of mass is closer to our, it is more towards our upper part because it's heavier. Okay, I will say when they are equal, of course, is going to be in the middle. This is how we calculate the center of mass. We can say, okay, I'm going to maybe rearrange this as x center of mass equal m1 x1 plus m2 x2 plus m3 x3 if I have, but I don't have, like I have only 2 in this example, and this is divided by the total mass. As easy as this. The center of mass can be outside the object. For example, here when we are talking about donuts or anything that having the same shape here is going to be outside. Where is the center of mass of a baseball bat located? Of course, since it is not a uniform object, it's going to be closer to the thick end where it's going to have more mass. Yeah, this is an interesting one. Like I have a disk shown below, and for uniform objects, the center of mass is going to be at their geometric center. Then if I have sphere, then it's going to be at its center like this. Now suppose the disk now is cut into half and the pieces arranged as shown. Where is the center of mass 2 compared to 1? Now when we have it as 2 pieces, we are a semi-sphere. We're going to find that like the center of mass for each one is going to be a little bit above the like near the top. Okay, and then here also is going to be near the top, and then since they are equal, then their center of mass is going to be midway between the 2 positions. Let's say this is A and B, and therefore is going to be higher than the initial one. Okay, here I'm showing you how to do a simple calculation related to center of mass. I have here a banana boat, and like 3 people roughly, they have equal masses. One of them is sitting from the left at 1 centimeter, and the other one at 5, and the third one is at 6. These are measured from the left hand end, and then I want to find the center of mass. Of course, this is x center of mass, m1 x1 plus m2 x2 plus m3 x3 divided by the total mass, and then the masses, they're gonna cancel. I can calculate the location of the center of mass to be 4 meters to the right, and of course is gonna be closer to the heavier, like where the accumulation of heavy. Here, we sometimes we need to predict if the object is gonna tip off or not. Here I have 3 boxes placed on a ramp in the configurations below. Friction prevents them from sliding. The center of mass of the box is indicated by the blue dot in each case. In which case does the box tip over? Now I want you to do this. Okay, this is usually what I will do. This is gravity. Oh, this is the gravity. Okay, then this is the center of mass, and you need to draw a straight thing. Now, if that force is gonna be within the base of the object, then the object will not tip over. For this one, clearly is gonna go in a way that is gonna tip over. Then number 3 is gonna tip over if the box can rotate, because this is going to be the torque created by the weight. Now here I have two also configurations of a book, and which of the following is true, which one is gonna tipping over. Case 1 will tip, case 2 both, neither. Of course, I will say case 1. If you look here, I did draw for you the textbook, and I did draw the center, because the book, we can assume it is a uniform a uniform mass distribution. Then in this case here, the center of mass is gonna be outside, or like it's not on the table, then this one is gonna tip over, this one is not. Okay, the center of mass here, we can assume, of course here, this is not a real situation where we're gonna ignore the rotation of the object. Usually we are not gonna get that situation. This is just considering translation. Here I am adding translation, which is the motion from the position with rotation, and I will say all the parts of the object, they are going to change their position during that process, except the center of mass. Then I will say there is one point that moves in the same path as the particle, which is the center of mass. And this is like a parabola that is going to show us as if it is like a projectile motion thing. Also, the general motion of an object always can be considered to be the sum of the translational motion of the center of mass plus rotational plus vibrational, or any other forms of motions above the center of mass. We will study more of this when we go to when we will move to rotation. Okay, here I am just showing you a derivation for total linear momentum of a system of particles. I will say the total mass times the velocity of the center of mass is going to be the mass 1 times v1 plus mass 2 v2 plus mass 3 v3. And from that, I can derive v center of mass to be m1 v1 plus m2 v2 plus m3 v3 divided by the total mass. Also, we can do the same thing for the net force, and from that we can get that the center of mass acceleration is going to be mass 1 times a1 plus mass 2 a2 plus mass 3 a3 divided by the total masses. Okay, now here also in Newton's second law, we can write it for a system of particles as m, the total mass of the system, equal times a, the center of mass, equals f net external. We use these usually in situations where we have separations or explosions. Then here I have this object, it was one piece, and then here it did convert into two pieces. One of them is taking this path and the other one is taking this path. But what is if we will be able to calculate what is the path of the center of mass, you will find that it's gonna follow this path here, which is gonna tell us that this one again is gonna move like that. The center of mass is gonna move in that parabola that is initially the projectile motion of a particle. Now, system with changing mass rocket propulsion. If a mass of fuel delta M is ejected, you know that is gonna burn and then it's gonna be exhausted out of the rocket. The change in the momentum because of that is gonna be delta P equal the change in mass times V. And then the force or the thrust is gonna be the change in momentum, which is delta M over delta T times V. Remember, we did talk about this when we introduced impulse at the beginning, and we said this is the more general equation where the mass can change. Now, this is extra fun. Like, I want you to look at it. For me, it's not required, but this is here is talking about the human body, and maybe one of the questions here is what about this location of the center of mass of the leg when it will be straight, or versus another position which is gonna be the, I will say, the bending one. And here you can see that in this like the high jumpers, they have developed a technique where their CM actually passes under the bar as they go over it. This allows them to clear higher bars than like the center of mass is going to be somewhere here, which is going to make them make it. This is here. You can try this to determine the position of the center of mass of the whole leg when it is stretched out like this and when it is bent at 90 degrees. It's a very straightforward direction, I will say, calculation, but just I don't want to go over it, and it's for you. And this is the summary of the chapter. It was such a long chapter. Okay, just look at it, and please watch the videos. Thank you and have a great day.